in A.
Hmm?
One of the names ends in A.
Yeah.
Okay, so now we've got two big topics that we need to cover. How you apply stoichiometry, electrolytic cells, and then also how you determine a different way to look at equilibrium. So you have to start with this, and this is on your equation sheet, and it's I equals Q over 2. So I is current, okay? So, and that's measured in amps. If you've ever seen like the breaker box in a basement or somewhere in your house, okay, you have different types of breakers that are rated at different numbers, okay? So it might be a 10 amp breaker, it might be a 15 amp breaker, things like that. So basically, if the current flowing through that breaker exceeds that limit, like if you have a 15 amp breaker and you try and put 17 amps through it, you throw the breaker, okay?
Is that when the breaker pops?
Yes, okay? Cars have breakers on them, okay? So you typically, if you've ever looked at a car, you can find like literally it has a similar type thing. It has like a box that typically has a list of all of the breakers, like for your windshield wipers, for your heater, for if you have electric doors, that type of thing, okay? So, and again, if you throw too much energy into it on a car, if you ever see it, it's going to look kind of like, they look like this, like yay wide, and they'll have a piece of metal in there. And if that metal gets too hot, it actually burns and burns through, and that's how you throw it out. So here's the point of the story. So when you look at a visual approach to this, so imagine that you have a dam and you have water stored up behind it, okay? So the height of the water is like your energy. So that's like volts, okay? So volts, remember, are joules per coulomb. That's how much energy there is per unit of charge. If you apply this to water, it would be how much energy there is on each drop of water. So the higher that water gets, the more energy that it has per drop. So the higher the volts are, the more energy that there is per coulomb. Okay? Now, current is basically the size of the pipe that allows the water to flow through. So in the classic example, you have two different sizes of pipe. You have a tiny little straw, and then you've got this big, massive concrete pipe. Okay? So in both situations, you're going to have the same voltage. Okay? So in both situations, the water is at the same height. So the water has the same voltage, same amount of energy per coulomb. If you have this little drinking straw, then you're not going to get very much water flowing down there. Okay? So your current is going to be small. So you can think of current as like a flow rate. It's units per, instead of meters per second, like how fast you're driving, or kilometers per hour, miles per hour, whatever that is. So instead of that, it's how much charge is moving per unit of time. Okay? So if you've got this little straw, not much water is going to flow through. It has a lot of potential, but it's not going to move a lot of water. Now imagine right beside it you have this big, massive concrete pipe. Okay? Same voltage. This is going to have a lot of current because you can get a lot of water through there in the same amount of time. Okay, so in electricity, the old adage is that voltage doesn't kill, current does. Okay, so you can have a tremendous amount of voltage and have a lot of energy, but if not very much of that flows, you're okay. But you can have a smaller current, but if you have a lot of electricity flowing through that per unit of time, that's when things go bad. So voltage doesn't kill, current does. Hopefully you never run into that situation, but if you happen to, I'm just saying. Now, here's how this works with what we're going to do. So let's say that you're going to have a container of molten aluminum. we've been talking about that. Okay? So there's certain numbers that you need. One is the idea that current is charged per unit of time. Now, we're also going to need Faraday's constant. Anybody remember this Faraday's constant?
96,485 coulombs per mole.
Oh, I just call it 96,500. Then what are the units?
Coulombs per mole.
Coulombs per mole of what?
Electrons.
Mole of electrons. Okay? So if you have a mole of electrons, 6.02 times 10 to the 23rd electron, and each electron has a certain amount of charge. And that's 1.60 times 10 to the negative 19th coulomb. So you take 1.60 times 10 to the negative 19, multiply that by Avogadro's number, you get about this number. Okay? So that's where that comes from. Michael Faraday didn't actually come up with it because, ironically, it's called Faraday's number. When Faraday did this, they hadn't found electrons yet. They said, hey, it's a good idea. So let's go with it. That's what they call it, Faraday's constant. Okay, so here's what I want to know. I'm going to run this system, and we're going to run this for 1 hour. And we're going to throw an electricity in there of 10 amps. So what I want to know is how many grams of aluminum I can produce. Okay? So you're an electrical engineer. Company has hired you, say, hey, we have it set up. We're gonna throw a 10 amp current into this deal. We're gonna have molten aluminum. And I want to know what should our production be in grams if we let this thing run for 1 hour. Okay? So at the end of the day, what units are you going to end up in? Grams of aluminum. Okay? Notice this is grams of aluminum. This is not grams of aluminum ions. Okay? This is grams of aluminum. So start with this reaction. You're going to have Al3 plus, and what's that going to do? It's going to add 3 electrons, and you're going to make aluminum. So here's what's going to be vital. It's subtle, but it's important. At some point, I know that the stoich is that for every 1 mole of aluminum, I'm going to consume 3 moles of electrons. Okay? It's a simple stoich, just like you've done stoich before. Only difference is that this is electrons and aluminum. Okay? It's the same stoich. 3 moles of aluminum or 3 moles of electrons will give you 1 mole of aluminum. Okay? Same ratio. We can use this. It's going to be good. Now, start with this. And I'm going to kind of show you the whole complex thought process. Then we'll work it all kind of in one big line. So you have 10 amps, right? So what does the 10 amps mean? So that's your value of I, right? Well, so what it means is that you have 10 coulombs per 1 second. Okay? That's what that number means. So if this thing ran just for 1 second, you'd have 10 coulombs of charge that ran through it. But it didn't run for 1 second. How long did it run? 1 hour. Or 3,600 seconds. 60 times 60 gives you 3,600. So one option is I sit here and go, okay, I want to multiply that by 3,600 seconds. Okay? Seconds cancel out. I get 36,000 coulombs. Okay? Cool. Now, I got that number. Nice. But I got to get into electrons. Okay, I got to mix electrons in here somehow. So we know Faraday's constant, right? So we know that if I start with this 36,000 coulombs, right? And we know Faraday's constant, which is 96,500 coulombs per mole of electron. It's coulombs. So if I come down here and go, okay, hey, that's 96,500 coulombs per 1 mole of electrons. So if I did this step, what would I get?
Moles of electrons.
Moles of electrons. Okay? So if you do this step, to save you all some math, you get 0.373 moles of electrons. Cool. Okay? Now I got moles of electrons using Faraday's constant. But I'm still not into aluminum. Well, I know this number, right? I know the ratio of moles of electrons into moles of aluminum. So then I could take that number, the 0.373 moles of electrons, and go, oh, right, there's 3 moles of electrons to every 1 mole of aluminum. Now, if I stop right now, what would I have?
Moles of aluminum.
Moles of aluminum.
80 grams.
80 grams. Here's a little Chem 1 story for you. I'm going to put 1 mole of aluminum down here, 27.3 grams up here. And if you do all that math, you get 3.36 grams of aluminum. Now, that's if you like to divide and conquer. Okay? That's a divide and conquer process. Some people like to divide and conquer. I don't. Okay? I like to do one big stoic problem. So if I were to do this problem, this is what I would do. I would start off with the 3,600 seconds. Okay? I know my time, right? Then I know my amps. So that's 10 coulombs per 1 second, right? So now I've got coulombs. Then my next cell, I'm going to go, okay, right? Hey, I got Faraday's constant, 96,500 coulombs per 1 mole of electrons. Okay, cool. I got that. I know for every 3 moles of chihuahuas, I get 1 mole of aluminum. And I know 1 mole of aluminum is 27.3 grams. Seconds cancel out, coulombs cancel out, moles of electrons cancel out, moles of aluminum cancel out. I'm left with grams of aluminum. Okay? So you can either do this as one big massive problem, which is cool, or you can divide and conquer. But now, let's say that's not much. It's like we're running this thing for an hour, and we get enough aluminum to basically make 3 paper clips. No, that is. A paper clip is like 1 gram. Okay? So we've let this thing run for an hour. Great. We can make 3 paper clips.
Cool. Let it run for 100 hours.
We can let it run longer. So if we want to increase production, we can let it run longer.
More current.
Oh, more current. Ooh. Now, if I bump this up to, say, instead of 10 coulombs, 10 amps, maybe I go 100 amps. Now, if I go to 100 amps, now I'm up to 33.6. But here's the engineering side of it. You want to run 100 amps. Great. What's your downside?
You increase upkeep or maintenance costs.
Yeah. I've got to buy a lot more electricity to run that thing at 100 amps. Okay? Because I get billed by my energy usage. So you really want to go big. Oh, hey, let's really go big. Let's go 1,000. Okay? 1,000 amps. That's a lot. That's a lot of paper clips. Okay? That's a lot of paper clips or a lot of aluminum cans. But again, here's the trade-off. And especially once you start cranking up to like 1,000 amps, that most, like your wiring in your house is rated up to like 15 to 20 amps. Okay? You do this like 1,000, you're running with the electrical big dogs at that point. Yeah. So that's your trade-off.
So at your house, you could make like 20 paper clips an hour?
Oh, you're typically, literally, probably current out of your house would be like 10 to 15 amps. So the biggest problem you would run into is making the molten aluminum oxide. Okay, this is the simple side of this. Getting the aluminum oxide and melting it, that's going to be the tough part. Okay, now, so these.
Okay, you know, like the power stations, do they cut down the current so that like 10 million amps isn't
They,
going
they,
to
they step down the voltage. Okay? They because it's easier to transmit very, very high voltage. Okay?
Yeah.
And then you step it down before it goes into your house.
So it doesn't blow up.
Okay, now, so problems like this play one of two ways. Either you're given the time and you're asked to find the mass that's produced, or they would say something like this, okay? They would say, all right, I want to make 5 grams of magnesium from molten magnesium ions, and I have like a 20 amp current, and I want to know how long I need to run this. Okay, so here's the other side of it. So with this one, it's kind of the reverse of what you have before. This one, you had the time, and you end up with the mass. And a problem like this, you start with the mass that you want, and you want to end up with how much time it's going to take for this to occur. So at this step, what's the last step going to be? What's your last conversion going to be? To end up in what? Seconds. So you want to make 20 grams of magnesium, right? Okay? So it's just basically the reverse process. Molar mass of magnesium is 24.3 grams of magnesium per 1 mole of magnesium. Well, what's the ratio between magnesium and magnesium ions and electrons?
2 electrons.
So for 1 mole of magnesium, that's going to require 2 moles of electrons.
Wait, don't you have 5 milligrams of magnesium instead of 20?
I'm sorry, my bad. I was looking at the ants. 5 grams. Okay. So now, if you stop now, what do you have?
Moles of electrons.
Moles of electrons. And then from here, you can go, okay, hey, Faraday's constant. You can go 1 mole of electrons is 96,500 coulombs. And then you have your amps, which is 20 amps. So you've got 20 coulombs per 1 second. So then your grams of magnesium will cancel out, your moles of magnesium cancel out, your moles of electrons cancel out, your coulombs cancel out, and you end up in time. Okay? So it's just one big massive story problem. All right. Last thing. And this is where a whole bunch of things are going to fit together. So this is one of those, hopefully, aha, tink moments where some random things all kind of come together. So visualize this. We're going to go old school. We're going to have a strip of zinc, salt bridge, copper. Zinc ions, copper ions. Okay? So, if I gave you this under standard conditions, hopefully at this point, you should be able to calculate E naught without batting an eye. Tell me which one is reduced and which one is oxidized. Okay? So let's do this. Should be old hat Burkamp. I got this. Look at your chart. Which one's going to be reduced? Which one's going to be oxidized? The copper or the zinc? Why? So Cu2 plus 2 electrons has an E naught value of what? What?
3.4.
Huh?
3.4.
0.34. I thought you said 3/4, and I'm going, what? Okay. Now, what's the reduction potential of zinc?
Negative
-0.72.
Negative what?
0.76.
Okay. So you should be able to look at those two numbers. Which one's reduced, what's going to be oxidized? Olivia Pruitt, which one's going to be reduced, which one's going to be oxidized?
I'm going to say something stupid. I don't know.
Just think about the other.
I It's gonna be copper because it has a higher E0 value, higher positive E0 value.
Yes. If you play the over-under game, copper is farther up. It wants to go in this direction. Okay? So the zinc is going to get what? Oxidized. So we switch this. This becomes 0.76 volts. We add those together. We get 1.10 volts. That's my E0 value. Okay, so we set this up. The theoretical value on that is going to be 1.01. Now we know my E0 value. True? Good. Over the period of time, what's going to happen to the concentration of the zinc ions?
Zinc ions are going to increase.
Why?
They're oxidized.
This gets flipped, right?
Yeah.
So over the period of time, I'm going to increase the concentration of my zinc ions. What's going to happen to the concentration of my copper ions? It's going to go down. So eventually, what's going to happen to the reading on that voltmeter? I'm going to make the solution more and more crowded on the zinc side. And I'm going to have fewer copper ions sending out text messages going big party. What's going to happen to the value on the voltmeter? It's going to get smaller, right? It's going to drop. The battery's going to run out. Eventually, I'm not going to have any copper ions left, and the solution on the zinc is going to be so crowded, Mother Nature goes, hey, I'm tapped out. Done. What would be the reading on the voltmeter at that point? You say this, because there would be no potential for the electrons to move. They got no copper ions, and you have a crowded hallway. Everybody goes, nope, I'm chilled out. No potential to move. Now, if you look at the Nernst equation, E equals E0 minus 0.0592 over N times the log of Q. Right? There's the Nernst equation. Old school. Okay? Old school. Now, here's the story. When it reaches equilibrium, instead of Q, what are we going to have? No.
What'd you say?
Once it reaches equilibrium, instead of Q, we're going to put another variable in there. K! Because what's the only time you use K? Oh, when it's at equilibrium. So I got E0 minus 0.0592 over N times the log of K. Now, once you reach equilibrium, what's going to be the reading on the voltmeter? Okay. Now, I want to isolate K. I want to get K by itself. Well, I hate subtraction. I'm going to add this monstrosity over here. Okay? So I'm going to have 0.0592 over N times the log of K is going to equal E0. Cool with that? See what I did? Nothing tricky. So what am I going to do to get K by itself? I want to multiply by, because I hate fractions. I want to multiply by N, and then I'm going to divide by 0.0592.
10 to the power.
So K, E0, and let me write it in here. Okay? Now, let's talk about this. Let's talk about this. This is where a whole bunch of random things will make more sense. Okay? So let's play a couple of scenarios. Let's say E0 is a negative number. Okay? Because that's the only thing up here that could possibly be a negative number. Okay? E naught is a negative number. What does that mean? Spontaneous, not spontaneous.
No bueno.
Oh, not spontaneous, right? So let's just make up a number. Let's say E naught is negative 0.50 volts. Okay? Let's just make up a number. Say it's negative 0.5. And let's say N equals 2. Maybe it's magnesium. Okay? N is going to equal 1. And that N is from the balanced reaction. Same N we've always used. Okay? So somebody take 10 to the negative 0.50 volts times 2 and divide that by 0.0592. Let me know what you get.
Dude, 10 to the power as well.
You're going to take 10 to the power of that whole thing.
Is it a really small number? Like
Yeah.
Like 1.28 to the negative 17.
1 point what?
28.
Times 10 to the negative.
17.
Okay. Wow. Now, flashbacks. Flashbacks. When we started this, middle of January, first week of January, we talked about Ka values.
No.
Ka values are big numbers or small numbers?
Small.
K numbers are small numbers. Maybe like 1.28 times 10 to the negative 17. Okay?
That's the case.
I'm gonna go up there.
It's
Now.
one circle.
Oh, it is. Oh, it's just going to be one sort. So your Ka is a really small number. If you look at hydronium ions turning into, or Ha turning into hydronium ions and anions, is this reaction favored? If it's a weak acid,
Oh,
is
no,
this
no,
forward
no.
It's
reaction
on the left.
favored?
It's on the left.
All
No.
the way around, pal.
So if you have a small K value,
Right.
throw it to a small number, this reaction is not favored. This is why it doesn't ionize. Oh. Now, what do you know about reactions that have a negative E naught value? Spontaneous or not spontaneous? Oh!
That's cinnamon.
If you have a negative E naught value, what does that mean? It's not spontaneous. Guess what? If you have a negative E naught value, what are you going to crank out? Really, really big K value, really small K value. Really small. Okay? Ah. Now, KSP. You look at magnesium hydroxide. Magnesium ions and 2 hydroxide ions. Okay? Magnesium hydroxide is insoluble. What do you know about KSP values? Big numbers, small numbers?
Small number.
Really, really small numbers. Is this reaction favored in the forward direction?
I don't remember.
No. This is why it's insoluble. This is why magnesium hydroxide forms a precipitate. So this is not favored. Guess what? KSP values are also what?
Small number.
Small numbers. Okay? Because they're not favored. Now, let's talk about hydrochloric acid.
Oh.
Hydrochloric acid fully ionizes?
Yes.
Absolutely. You get hydronium ions and chloride ions. What do you know about K values for
Massive.
strong? Massive.
Massive.
Oh, massive. You know why? You know why? Go back up here. Check this action. You put a positive E naught value in there.
Oh, you're gonna get a big number. Oh, cinnamon. That checks out.
Okay? So if E naught is positive, that means the forward reaction is favored, which means you're going to get really big K values. So check this. What if E naught equals 0? What's 10 to the 0 power? Oh. So if E naught equals 0, K equals 1. Guess what? System's at equilibrium. So if K is a really, so listen to me. Listen, if you remember nothing out of today, you remember this. If K is big, that corresponds with a positive number for E naught. That means that that's a spontaneous reaction. If you have a small K value, that corresponds with the negative E naught value, and it's non-spontaneous.
It's not favorable.
But it's favored in the reverse.
That's awesome.
Like that? Okay. On this assignment, there are 2 problems out of the book. Okay? None of this gets done on this sheet of paper. None of this gets done on this sheet of paper. There are 2 problems from the book, page 889, 95, and 96. Everything else that's on here, only do the ones that are circled. Okay? Only do the ones that are circled. Now, when you get to 71, it says understand the conditions for which reactions occur if any of the following operations are performed. Now, I circled this because it was crappy where they put the instructions. So think of this up here. It says for the reactions that occur, only for the ones that occur. Write the balanced equation, calculate E naught, delta G naught, and K. Okay? So, for the reactions that occur, and do not randomly write down numbers and think, I'm going to know what they're going to mean. You write them out. E naught is this, K is this, delta G is this. Okay? But that's only for the ones that occur on 71. On 75, you're going to try and calculate a KSP value. When you get done, should your KSP value be a big number or a small number? Small. There you go. Just keep that in mind. Okay, we're done.